Right now, inside a building somewhere in Taiwan, a machine the size of a school bus is shooting a laser at a droplet of liquid tin, 50,000 times per second. That laser converts the tin into plasma, which then emits a specific wavelength of light. That light is reflected off a series of mirrors so precisely polished that if you scaled one up to the size of Europe, the largest surface imperfection would be less than 1 millimeter tall. And that light, that impossibly controlled beam, is then used to draw circuits onto silicon. Circuits so small that roughly 50 of them could fit across the width of a single strand of human DNA. This is 2-nanometer chip manufacturing, and it may be the most technically complex thing human civilization has ever attempted. By the end of this video, you'll know exactly how it's made. Think about every device you've used today: your phone, your laptop, the smart TV in your living room, the navigation system in your car. Every single one of them runs on semiconductors. But the chips being built right now, 2-nanometer chips, are different from anything that came before.
These aren't incremental upgrades. They are a generational leap. A 2-nanometer chip can pack somewhere in the range of 50 billion transistors into a space the size of your thumbnail. 50 billion. To put that in perspective, if every transistor were the size of a grain of sand, a single chip would contain enough sand to fill over 60 dump trucks. The global semiconductor industry generates over $600 billion a year. It underpins artificial intelligence, cloud computing, military systems, autonomous vehicles, and medical technology. But only a tiny handful of companies on Earth are capable of manufacturing at this scale. TSMC in Taiwan, Intel in the United States, Samsung in South Korea. And the gap between them and everyone else is enormous, measured not in years, but in decades of accumulated knowledge, infrastructure, and intellectual capital. Most people have never seen the inside of a 2-nanometer fab, and there's a reason for that. It all begins with sand. Ordinary-looking beach sand, except not ordinary at all. Specifically, quartzite sand deposits found in places like Brazil, the United States, and Australia. These deposits contain silicon dioxide at a purity level of around 99%.
But for semiconductor manufacturing, 99% isn't even close to good enough. The silicon used in chip manufacturing must reach a purity of 99.9999999%. That's 9 nines. One impurity atom per billion silicon atoms. To achieve this, the raw sand is smelted in an arc furnace at temperatures exceeding 1900 degrees Celsius, reacted with hydrogen chloride gas, distilled multiple times, and finally reduced back into elemental silicon using the Siemens process. The result is a chunk of polycrystalline silicon that looks like a jagged metallic rock. But that's just the beginning. That polycrystalline silicon gets loaded into a quartz crucible inside a device called a Czochralski puller, named after the Polish scientist who invented the technique in 1916. A small seed crystal is lowered into the molten silicon, which sits at just above 1,414 degrees Celsius, silicon's melting point. Then, very slowly, the seed crystal is pulled upward while simultaneously rotating. As it rises, silicon atoms from the melt latch onto its structure, growing the crystal layer by layer. Over the course of roughly 24 to 48 hours, this process produces a perfect single crystal silicon cylinder called an ingot. A typical ingot for advanced chips is 300 millimeters, about a foot, in diameter, and can weigh 100 kilograms. The crystal structure within it is flawless, atom by atom, end to end. It has to be. Any disruption to the crystal lattice at this stage will cascade into defects later in the process, destroying chips that won't be discovered as defective until days or weeks later. The ingot is then sliced into wafers using a diamond wire saw, each wafer about as thick as a credit card, then chemically polished to a mirror finish, so flat that the variation across the entire surface is measured in single-digit nanometers. Now, the real work begins. Each wafer will eventually become hundreds or even thousands of individual chips. But first, it must go through a process called photolithography. And this is where the manufacturing stops being extraordinary and becomes something closer to science fiction. The goal of photolithography is deceptively simple. Use light to draw a pattern onto the wafer. But at the 2-nanometer scale, this becomes one of the hardest problems in applied physics. The patterns being drawn are smaller than the wavelength of visible light. You cannot use ordinary optics. You need something different, something that pushes the boundaries of what matter and energy can do. Enter EUV, extreme ultraviolet lithography. The machines used for EUV lithography are built by a single company on Earth, ASML, headquartered in the Netherlands. Each EUV machine costs approximately $380 million. They weigh around 180 metric tons. They require a dedicated power supply, roughly equivalent to powering 3,000 homes. And there are fewer than 200 of them in existence worldwide. When TSMC wants more, they get on a waiting list. Inside the machine, that laser tin plasma system generates light at a wavelength of 13.5 nanometers, deep in the extreme ultraviolet spectrum, invisible and capable of being absorbed by almost everything, including air, which is why the entire optical path inside the machine operates in a vacuum. The EUV light bounces off a series of mirrors, up to 11 of them, each coated with alternating layers of silicon and molybdenum, each layer precisely 7 nanometers thick. The reflectivity of each mirror is around 67%, which sounds mediocre until you realize that achieving 67% reflectivity at EUV wavelengths required a decade of materials science research. Any contamination of even a single mirror, a single molecule of the wrong substance, can degrade the entire system. The light passes through a mask called a reticle, which contains the circuit pattern to be printed. It then gets focused down and projected onto the silicon wafer, which has been coated with a light-sensitive chemical called photoresist. Where the light hits, the photoresist changes its chemical structure. Where it doesn't, it stays the same. Then the exposed wafer goes through a chemical bath. The changed areas of photoresist wash away. What remains is an incredibly precise stencil, the ghost of a circuit, etched in chemistry on a silicon surface. One wafer will go through this process, with different patterns, dozens of times. Each pass adds another layer to the three-dimensional architecture of the chip. Modern chips don't just have circuits printed on their surfaces, they are built in layers, stacked vertically, like a microscopic skyscraper. After each lithography step comes etching. The exposed silicon, the areas where photoresist was removed, gets bombarded with plasma in a process called reactive ion etching. Charged particles carve precise trenches and structures into the silicon surface with sub-nanometer accuracy. The gases used include fluorine, chlorine, and bromine compounds. The chamber conditions, pressure, temperature, gas flow, electrical fields, are controlled to tolerances that would have been physically impossible to achieve 20 years ago. Then comes deposition, adding new layers of material. Atomic layer deposition, or ALD, adds material one single atomic layer at a time, using chemical reactions that deposit exactly one monolayer of material per cycle. A cycle takes a few seconds. To build a layer just 5 nanometers thick of a certain material might require over 50 sequential cycles. The uniformity across the entire wafer must be within a few percent, atom by atom, edge to edge. Then doping. Tiny amounts of boron or phosphorus atoms are implanted into the silicon using ion beams to create regions of positive and negative charge, the fundamental mechanism that makes transistors work. Too many dopant atoms and the transistor shorts. Too few and it doesn't switch. The margins are measured in individual atoms per cubic centimeter. And here is where we need to talk about the transistor itself, because what's being built at the 2 nanometer node is no longer the transistor you learned about in a physics class. For decades, chipmakers used a design called a FinFET, a fin-shaped three-dimensional transistor. It was a revolution when it debuted. But at 2 nanometers, the fin is simply too small to work reliably. The quantum effects become uncontrollable. Electrons start tunneling through barriers they're not supposed to cross. So the industry moved to a completely new architecture called gate-all-around, or GAA. In a GAA transistor, the gate, the switching mechanism, wraps completely around a stack of ultra-thin silicon ribbons called nanosheets. These nanosheets are just 5 to 6 nanometers thick. The gate controls electron flow from all 4 sides simultaneously, dramatically improving electrical performance and reducing power leakage. Building a GAA transistor requires patterning, etching, and depositing materials at tolerances that stretch the limits of atomic physics. And at 2 nanometers, a single chip contains 50 billion of these structures, each one built to near atomic precision. Every single one. This is the most impressive part of what happens in a chip fab. And it's not a single machine or a single process. It is the accumulation of tolerance. Each individual step in the manufacturing process introduces some degree of variation. A temperature slightly off, a gas flow marginally different, a mirror that has picked up a stray molecule. Each variation alone would be meaningless, but stacked across 600, 700, even over 1,000 individual process steps, which is what building a 2 nanometer chip requires, these variations compound. Managing this accumulation across an entire wafer, across an entire fab, across millions of chips per month is a computational and engineering challenge with no parallel in human manufacturing. TSMC's fabs run 24 hours a day, 7 days a week, 365 days a year. The clean rooms, where all of this happens, are filtered to Class 1 standards, meaning fewer than 1 particle per cubic foot of air larger than 0.5 microns. For reference, a hospital operating room is Class 10,000. The engineers inside wear full body suits, bunny suits, that cover every inch of skin and hair, because a single flake of dead human skin falling onto a wafer can destroy an entire region of chips worth thousands of dollars. The air inside is replaced entirely, hundreds of times per hour. Quality control at this scale operates at a level of obsession that borders on the philosophical. Automated optical inspection systems scan every wafer after every critical step, using AI-powered vision systems to detect defects as small as a few nanometers. Electron microscopes are used routinely, not for research, but for production quality checks. And even with all of this, not every chip makes it. Yield, the percentage of functioning chips on a wafer, is one of the most closely guarded secrets in the industry. For a mature 5 nanometer process, yields can reach 80 or 90%. For a brand new 2 nanometer process, early yields are believed to be dramatically lower. This is why new nodes are so expensive to bring online. Every defective chip represents not just lost silicon, but hundreds or thousands of dollars in processing cost that cannot be recovered. When chips fail testing, some can be partially salvaged. A chip designed to have 8 processing cores that has 2 defective cores might be sold as a 6-core chip at a lower price. Nothing goes to waste if it can be avoided. The economics demand it. Now, here are some numbers that will make you stop and think. A single TSMC gigafab, their newest facilities, costs over $20 billion to build. That's more expensive than most nuclear power plants. The fab in Arizona that TSMC is constructing in partnership with the United States government is estimated to cost $40 billion across multiple phases. The lead time to build a new fab, from groundbreaking to first silicon, is typically 3 to 5 years. That means decisions being made today about fab capacity will affect chip supply in the late 2020s. A single EUV machine contains over 100,000 individual parts. It is shipped from ASML in the Netherlands in roughly 40 shipping containers. It takes weeks for a team of engineers to assemble and calibrate on site. The electricity consumed by a large semiconductor fab is roughly equivalent to a small city, 100 to 200 megawatts continuously. Water consumption can reach tens of millions of gallons per day, which is why water recycling systems are a critical part of fab infrastructure. And despite all of this complexity, at full production capacity, a leading-edge fab can produce tens of thousands of wafers per month, each wafer yielding hundreds of chips, each chip containing 50 billion transistors. TSMC currently manufactures chips for Apple, NVIDIA, AMD, Qualcomm, Broadcom, and hundreds of other companies worldwide. Over 90% of the world's most advanced chips, below 5 nanometers, are made in Taiwan. That geographic concentration is one of the most significant geopolitical vulnerabilities in the global technology supply chain. Intel, after years of falling behind, is fighting back with its Intel 18A process, its own 2-nanometer class technology, incorporating gate-all-around transistors and a novel backside power delivery system called PowerVia. If Intel succeeds, it would become the first American company capable of manufacturing at the frontier since the mid-2000s.
Samsung is pursuing its own 2-nanometer process, called SF2, with volume production targeted for the coming years. The global race for 2-nanometer supremacy is not just an engineering competition. It is a strategic contest between nations, corporations, and competing visions of who controls the foundational infrastructure of the digital world. When that finished wafer comes out of the fab, it is tested electronically, every chip, every connection, every transistor pathway. It is then cut, or diced, into individual chips using a precision diamond blade or laser. Each chip is mounted into a package, a protective casing with electrical contacts, using wire bonding or flip chip techniques. The package is tested again. Then it ships. That chip, which began as beach sand in Brazil, became a flawless crystal pulled from a molten pool in Taiwan, was patterned by plasma and EUV light through over 1,000 individual process steps, was tested and verified and packaged, ends up in a device in your pocket. It runs at over 3 billion cycles per second. It contains more transistors than there are stars visible to the naked eye from Earth.
And it costs less than a cup of coffee to manufacture at scale. From a grain of sand to 50 billion transistors. From raw Earth to the engine of artificial intelligence, digital communication, and modern civilization. That is what happens when human ingenuity is pushed to its absolute limit. If you made it this far, here's something to sit with. Every 2 years or so, the industry moves to the next node. After 2 nanometers comes 1.4 nanometers. After that, something called 1 nanometer, a scale at which individual silicon atoms are only 3 or 4 atomic diameters apart from each other.
At that point, the laws of quantum mechanics don't just complicate the engineering, they rewrite it entirely. What manufacturing secret in this video surprised you the most? Drop it in the comments. I read every single one. And if you want to go deeper into the machines, the materials, and the manufacturing processes that power our world, subscribe, because we're just getting started.